Next, we are going to talk about the ring synthesis of Pyrrole. Similar to furan and thiophene, the most common ring synthesis of Pyrrole starts from the 1,4-dicarbonyl compounds, which is the electrophilic sites. And then in this case, you need to have the nucleophilic nitrogen source, such as an amine, in order to form the Pyrrole ring. If you use ammonia as a nucleophile, in this case it's called Pyrrole synthesis, the nitrogen can attack at the carbonyl group, and then you form the tetrahedron intermediate here, which can the nitrogen can further react with the carbonyl group, and then you form another tetrahedron intermediate here. After removal of water, you form two enamine-like structures which completes the aromatic system, and then you get the Pyrrole. In this example, you can see that you don't need to start from the ammonia. You can have primary amines that connects to some groups, and finally you will get the Pyrrole that has N substituents. And you don't need to use the 1,4-dicarbonyl compound. This one is the masked 1,4-dicarbonyl compounds in the acetal form. So under acidic conditions, this one can lose methanol, and then you form the electrophile like this, which your amine can now attack. And then if you draw out the mechanism slowly, eventually you will get to the Pyrrole. Another way to synthesize Pyrrole is by using NOR synthesis, which has two components. The first one is the alpha amino carbonyl group, which provide the source of nitrogen in the form of amino group, which is nucleophilic. And this will react with another molecule of ketone, and eventually you are going to form the enamine at this position. So this one will be nucleophilic, and eventually this will react with a carbonyl group on the alpha amino carbonyl compound. After removal of water, this will form the aromatic system, which is Pyrrole. As you can see in the bottom example, the amine amino group reacts with the carbonyl group here, and then you form the enamine, and the enamine here can react with the carbonyl group here, and removal of water to form the Pyrrole. And you can see that under basic conditions, some of the esters can be hydrolyzed, and then at high temperature you can also decarboxylate these carboxylic group. So if you have a base, you remove the proton here and Higgs electron here and Higgs electron here. If you use harsh conditions enough, it will force the carbon dioxide to remove from the molecule and generates an anion. And this anion on the sp2 can get protonated during the workup steps in order to form the non-substituted Pyrrole at the end. So you can see that if you introduce the ester group to make the reaction goes faster, you can also choose to remove it at the end by decarboxylation. Okay. If you want the non-substituted Pyrrole as the product, you might need to use an aldehyde to start with, but most of the time the aldehyde is not so stable. For example, if you want the aldehyde here, it will self-condense with the nucleophilic amino group, so you can protect it as the acetal, and the other part also you can protect it as an enol ether here as well. But when it reacts, the amine can now attack here and then undergo addition elimination to form the intermediate that is quite stable. If you don't put any acid in there, the acetal will stay like that. So you can isolate this intermediate out and then put it under acidic conditions, which will protonate here to form the good leaving group and kick out. And this will generate the good electrophile here that the enamine can now attack. And after removal of methanol, this will give you the unsubstituted pyrrole. Another way to synthesize pyrrole is by using isocyanides, which will provide 3 atom component into the pyrrole ring. Another component, you need 2 carbon system, which can be an alkene, which needs to be activated by either the carbonyl group or nitro group. You can see that in this case, you will need some leaving group, such as torsyl group here, or the nitro group itself, in order to generate the unsaturation later on, so that you can eliminate out and forms the alkene. The mechanism of this reaction starts from the deprotonation using base at the alpha position of the isocyanide group, because here the negative charge is stabilized by both the torsyl group and the isocyanide group. This negative charge is nucleophilic, which can then attack at the beta position of the alpha-beta unsaturated ketone, which will generate the enolate here. And this enolate is nucleophilic. This will attack at the terminal carbon of the isocyanide. You may think that the isocyanide here has the negative charge at the carbon, but why is it electrophilic? Because if you draw out the resonance structure between this, it has another resonance structure with carbene character at the carbon, which has only 6 electrons, right? So that's why the this carbon is now electrophilic. Okay, after attacking, you are going to form carbon that has now 8 electrons, which is now good. The anion here is in the sp2 orbital, which is quite basic. Now you can use this anion to remove the proton at the alpha position here to generate a more stable enolate anion. And you can remove the torsyl group as a leaving group and forms the pyrrole as a final product here. If you start from the alkene with nitro group, eventually you can remove the nitrous acid out from the reaction as well. So this nitro group can act as a leaving group as well. Another synthesis of pyrrole is by using Piloty-Robinson synthesis, utilizing the hydrazine as the source of nitrogen, and this is going to react with the ketone here. So first the nitrogen will attack the first ketone, and you are going to form the enamine, which another nitrogen can now attack the second molecule of ketone, and this you will form another enamine on the other side. And you have 6-membered ring that can undergo 3 free sigma tropic reaction. From here, you have kind of like the 1,4-dicarbonyl compounds that already have nitrogen. So eventually, if you draw out some of the condensation reactions, eventually you are going to form the Pyrrole. The nitrogen that you have doesn't need to be only the hydrazine. You might already have some substituent on the nitrogen, and at the end you are going to get the N-substituted Pyrrole as the final product. And the left hand side and right hand side doesn't need to be symmetrical. You can start from one side having an oxyl group and the right hand side having 2 N-propyl group, and eventually you will get the unsymmetrical Pyrrole as the final product. The last example for the synthesis of Pyrrole starts from an alkyne, which will provide 2 atoms to the Pyrrole ring, and the oxidoxazolium, which will provide 3 atoms to the Pyrrole ring. Okay, and the reaction starts by using the nucleophilic carbon here of the kind of like the enolate to attack the alkyne, which will give kind of like the enolate here that will attack the iminium type component. So eventually you are going to form the bicyclic as the intermediate here, and you can see that there is a carbonyl and ester group that can be decarboxylated quite easily into carbon dioxide, and this one can undergo electrocyclic reaction to remove the carbon dioxide, and at the end you will get the Pyrrole as the final product.